Welcome to Chapter 13. Chapter 13 is called Simple Linear Regression. And what it is drawing straight lines and taking a scatter chart and turning it into what's called least squares regression, the line that has the least amount of error. So we are going to have the coefficients of the intercept, which is B0, and B1, which is the slope. And so it's determining where the y-intercept is and the slope of the line. So you can use it for predicting. When I teach supply chain, it is used to predict, to do forecasting into the future, how many you're going to sell, not just next period, but it's one of the few techniques that allows you to project down the road. And by down the road, I mean not just next time period, but the one after and the one after and 7 years from now if you want. So you have the dependent variable, which is a variable we wish to predict or explain, and the independent variable. So a very simple example of this would be the independent variable is time, which is your x-axis, and the dependent variable is your y-axis, which would be sales. Or it could be something like population. We all know the population of the world is growing at a certain rate. So you can determine, and if it's linear, it tends to be more of a curve, but the growth rate can be linear. But in this case, so you would have time as your x-axis, and whatever's on the y-axis is your dependent variable. So sales are based on time, or sales are based on number of contracts that you sell or get. So you can use the scatter chart, just X and Y, just like you've seen for years and years. So in this particular case, you have various types of relationships. The closer the dots are to the line, the stronger the what's called correlation between the two. You want the line to be drawn, it's the minimum amount of distance from each one of the dots. So you have positive, which is upward sloping. You have downward sloping, which is the one in the top right-hand corner. So that means they move in opposite directions. So an example of this would be a positive correlation, let's say for a house, would be the fact that the larger the house, the more it sells for. A negative correlation would be the fact that the older the house, the less it sells for. You can also have curvilinear relationships, and we're just dealing with linear relationships, by the way. And then there's no relationship, which means it's unexplained, or it's the slope is zero. It means there's no relationship. So a flat line or horizontal line would have no relationship, or you can see the bottom left-hand corner, it's just all over the place. You can draw a line, but the gaps between the dots and what the line would be so massive you're not explaining anything. There's only one independent variable, and in this case, in this chapter, we're only going to deal with one dependent variable, because there's a lot of factors that can affect the selling price of a house. All right. So what you have is, as I mentioned before, the predictor for y is the slope, which is B1, times the independent variable. So how many is it? Period 2, period 5, period 12. You have the B0, which is the intercept, and then you have the random error. And so in this particular case, what you're trying to do is you've got the y-intercept, which is on the far left-hand side here. Then you have the slope of the line, and this line is drawn not as a guess, but it has the least amount of distance between the dot and the line. And like I said before, that's called least squares regression. And that's the only one that we use because it's the best. It gives us the best results. So you get a slope that for every change in y, it's caused by 1 unit increase in x. So The formula is that we're going to use is B0 plus B1 times the time period for X. Here is the formula. Once again, Excel has this built in, so we don't have to bother with all this math, all of these calculations, which quite frankly do not add value. If you think you're going to get paid a lot of money to calculate numbers, you're not. You're going to get paid a lot of money to know which tool. Just think about all the things you've learned so far in this course. Mean, mode, median, way back then, probabilities, hypothesis testing, confidence intervals, things along this line. And some of these you won't use a huge amount or very often, but even knowing they're there, even knowing that there is, let's in 5 or 12 years, and you're working and you say, well, I need to do a sample. You can realize that you have to be able to determine the sample size. So you don't sample too few, or you don't sample too many observations, because that can cost you in both ways. Too few, not solid enough results. Too many, it didn't add extra value. So again, these calculations, that's not important. And then you also need to know what the results mean, which is what I've tried to focus on. So B0 is the estimate of the mean value of Y when X is 0, which is a fancy way of saying the Y-intercept. And B1 is the slope. It's the estimated change in the mean value of Y as a result of a 1 unit increase in X. So in this particular case, they happen to use housing prices and square footage. So just what I was mentioning before, they take a random sample of 10 houses, and you can see that you've got the price and you have the square footage. We plot that and it looks like this. So it's, as we would expect, the larger the house, the more it sells for. That's, for anybody who knows anything about housing, that makes common sense. If you want a bigger house, you have to pay more, generally. But it's not the only factor. And in chapter 14, we'll deal with the exact same thing, except it's multiple regression. So it won't be just square footage. So here we have the results on our ANOVA table. We have the y-intercept, which is 99.24. We have, for every square foot, the coefficient is 0.10977. So what you would do in this particular case, so let's say that you have a 1,000 square foot house. You put in the 1,000 in the very back part of the formula, up at the top here, multiply by 0.10977, and add it to 98.24833. And that tells you that the expected value of the house. So this will be given to you. I'll show you how to do it in the example, so you know how to create this ANOVA table. But the interpretation of it is what's really important. So then there is our line. The 99 plus the 0.1 times the square footage. So that will give us, at least within that range, from 1,000 to about 2,500 square feet. Yeah, this is what we can expect is the selling price. And information like this would be, say, given to realtors. It'd be a factor as to what they, a lot of times realtors are asked to, what's my house worth? Well, there would be a factor. They would look at comparables, but, and they would look at a lot more things than just square footage, which is the exact same concept, except we'll deal with in chapter 14 what's called multiple regression. So it's the number of square feet, it's the age of the home, which would be a negative, the number of, say, bathrooms, the, is it on the corner, things along this line. So in this particular case, it's a fairly simple concept. And these days, I remember when I went to university, we had to calculate this by hand. Oh, it was long tedious, boring, and just difficult to get the right answer because there's so many calculations that go into it. No way I'm gonna ask you or show you how to do that. All right. That's not the way it's done in industry. That's why. Not because I personally believe it's an outdated way of doing it, which it is, but industry says we want students who can use the technology, not just using the technology, it's way faster and it's way more accurate. I know when I started using technology in my supply chain classes, I got to ask over double the number of questions and the class average went up 8%. That's kind of like win-win. All right. So in this particular case, a 2,000 square foot house should sell for $317,850. Simple as that. If the house is 2,500, we plug the 2,500 into where the 2,000 is, multiply, and then add it to the 98.25. And as you can see, just a little word of caution. If you start getting in beyond, like the sample went from basically 1,000 square feet to 2,500. If you start to try and predict below or above that data set range, it may not be linear. So it's just a little point to be careful of. It doesn't mean, oh, I got a 4,000 square foot house. I just plug that number in and away I go. So you've heard about relevant range. That's what relevant range means. In this case, our relevant range is from 1,000 to 2,500 square feet. Just a little important factor. Now, I left this slide in to show you what you would have had it done, but what Excel will do for you. And yeah, just looking at this sends, quite frankly, bad memories, shivers up my spine. It's like, oh, yeah, these are the calculations that we used to have to do by hand. And a lot of students are still doing them. I don't know what percentage of students use Excel for statistics, but I think there's only one of the three major schools in Calgary that it is now the standard. So, and once again, industry says they want that. I've emphasized it over and over again. I'll try to stop beating that point. Is industry says don't teach them how to use, don't teach them the formula. Teach them the technology that has the formula built in, and you can do the answers in way less time, especially if you do the answer and then you want to change like a number or two. Yeah, that's called productivity. So here's all the math behind it. Again, this is just incredibly out of date, but I again want to show you how a lot of the students, I'd say probably 90% of students in Canada are still in stats, or at least 80 are still doing it this way. Fortunately, you're not part of that group. Yeah, just look at the numbers. Like I said, I left this in just to say, oh, I really am glad we're not doing it that way. Okay. So just like before, for the total sum of squares, you have the regression sum of squares and the errors. So the explained and the unexplained variation. So SSR is the explained variation, and SSE is the unexplained. So we don't know what's causing the change in housing prices. So in this particular case, if we just are using square footage, we already know, oh, things like interest rates can affect the house. What the economy is like, all these other factors. So, but we're just going to use square footage, and we're going to see what percentage is of the final price for the house, or the selling price, is caused by the square footage. It can be the most important. So here's our nice graph on it. We have the explained and the unexplained. You have the regression factor. All right. So the explained SSR explains the 18,934, and the unexplained is 13,665. For total error, or total variation, sorry, of 32,600. Now, what's really important with this is not the SSR and the SSE. It's the ratio between the two, and something called R squared. So what they do is they take SSR, so the regression, the sum of the squares, and they divide it by the total squares. So your SSR divided by SST gives you R squared. This is the important number. When you look back, what did that mean? Honestly, it's not really a big deal. You're looking for the ratio. So what percentage of the total is explained by SSR, which in our case is the square footage of the house? So if you have a relationship of 1, it's perfectly linear. And it can be, so every dollar change in the price of a house is caused by the square footage, which we know intuitively is not correct. There are other factors, but we want to see, is it like 63%? Is it 81? Is it 24? So the further that is, or the closer it is to, if it's 0, means there's no relationship. And you can see any value between 0 and 1 means it's partially explained. So we want it to be as close to 1 as possible. That's a good model. Closer to 0 is even to the point of being useless. So if there's no relationship, R squared is 0, which means your model, and what that would mean is square footage has no influence on the selling price of a house. That's what it means. So for example, if you included the weather, the temperature, well, intuitively, like, what does the temperature have to do with the price of a house? It would show up as a 0. So the R squared value is 0.58082. What that means is 58.08 of the variation is explained by square footage. What it also means, based on our model, is 42%, or 41.92 to be exact, is not explained by our model. So 58% of the reason why the price of a house changes is explained by the square footage. That's fairly simple to understand. And obviously, because it's over 50%, it's the most important factor. If anybody, yourself or parents or somebody you know has looked to buying a house, you know that the larger the square footage, the more you're going to have to pay for it. That is just, but it's not, again, the only factor. Here are, again, the nasty formulas. So I'll quickly go over that because I don't like looking at them. And here's some more, okay? The standard error, again, is calculated, but what does it mean? All right, it's measured, it is a measure of the variation of the observed values in the regression line. So if you have a small SYX, it's relatively small relative to these houses in this price range. The larger the SYX is, there's a lot more variability. So it's like standard deviation and variance. And you want the least amount of variation. All right. So what you're going to also look at is the relationship actually linear? And you also look for the independence of the errors. You look for the normality of the errors and the equal variances. So again, the software will do the calculations for us. So what we're trying to do in this case, and I'll get to it again in a moment, is we're trying to see if the slope is statistically significant. And once again, we'll look at the p-values. Right? Again, here's some of the formulas. Always B1 is there's no relationship. In other words, it's a horizontal line, which means that X has no influence on Y. You do a hypothesis test, to see if the relationship does exist. So in other words, the relationship is not 0. And all of this math will be simplified by looking at the p-values, which is why you did that earlier in the term. So you've got your data, you've got your same as before, you've got the slope, everything's the same. And now you look for, it gives you the test statistic or the t-value and standard errors and stuff like this. And what's really important is the p-value. You have a rejection region on the left and right, so it's two-tailed. And you're testing again to see, you're testing B1. What is B1? B1 is the slope. You want to see if the slope has meaning or if it's a straight line. It's a horizontal straight line. And here's the p-value. So what you remember from previous, this has a p-value of 0.01039, so just over 1%. You reject HO, which is actually good. Because remember, HO says at the top there, B1 is 0. So in other words, B1 equals 0, B1 has no effect. You want B1 to have an effect, otherwise you just take it out of your model. If, like the example that I mentioned about weather, if you include weather or the temperature, then you know it's a waste. It actually clutters or makes your model worse than if you just include square footage, number of bathrooms, number of bedrooms, things along this line. So there is sufficient evidence that the square footage affects the price of the house because the p-value is less than the level of significance. The level of significance is 5%. So the p-value is less than the level of significance, which is actually what we want. And you also can do that for the intercept. So the intercept is 0.12892. So you're not sure that the intercept is correct, has meaning, but that's really the slope or the B1. And when we next chapter, when we deal with B1, we'll have B1, B2, B3, which are just the different factors, but the exact same analysis. And using Excel, we can easily do multiple regression, not just single regression. But it's really important just to, with single regression, oh, okay, square footage causes the price of the house to go up. And I'm almost actually 99% sure that that's correct. Remember, the p-value is the rejection region. All right. And so this is the test for the slope. Once again, focus on the p-value here, which is 0.01039. That's the size of the rejection region. That's the probability of it not having an effect. And again, all of this is showing on this as we will create in our examples. The Excel, this printout comes right from Excel, but it's reading the results. So this is again the old way of doing things, which you can learn on your own if you want. I can explain it to you, but students have told me repeatedly, basically universally, oh, just have to focus on p-values. Yes, and you'll get the exact same answer if you use the old way of doing it, which was critical values and test statistics. You get the exact same answer every single time, like 100% of the time if you use p-values. So in this particular case, we can see that it gives us the p-value, and look, it even gives us the confidence interval. 0.03374 is the lower limit for square footage. That means the slope would be as little as that number, 0.03374, rather than the 0.10977, or it could be as high as 0.1858. So just over 3% to just over 18% is the possibility of what the slope really is. So you can see at the bottom, there's a 95% level of confidence that the confidence interval for the slope is basically just over 3% to just over 18, close to 18.5. And so it even gives us the printout of the lower and upper confidence intervals, and it tells us that it is statistically significant. So that's what's really powerful about this. And we're also 95% confident that it doesn't include zero. You learned or saw before that if the number is not within the confidence interval, that you would reject it. Zero is not between 0.03374 and 0.1858. So you would reject HO, which is good in this particular case because we don't want it to be zero. Zero means, again, it has no meaning. All right. Again, here's some more formulas. I left these in, and I'll ask you throughout the courses, like, after doing it this way, and I've completely revamped the course, do you want me to take these out? But I just thought show people the highly complex math that's behind this. All right. And are you going to get tested on this? Will probably be your next question. No. You're going to get tested using Excel. You're going to get tested on interpreting the results. All right. So if you want to do a confidence interval for this, you've the predicted price of the house is the 317.85. And you can do a confidence interval using the 0.03 and the 0.1858 to get the 280 to 354. So you're 95% sure the house is going to sell within this range, but that's a pretty big range for this house. That doesn't, I mean, the owners are going to look at you on the low end, it's going to be 280. On the high end, it's going to be almost 355,000. So if you need to sell the house for at least 280, you should be good to go. And you're not likely to get above 354. I mean, I would think that most realtors aren't, most realtors from their experience will will say, okay, the place you can expect about 430, but every once in a while, you get somebody who comes along who really wants the place and drives up the price, or there's a bidding war on that particular place for whatever reason, and that 430,000 you thought you were going to sell it for, you sold it for 452. I know a couple who were told a price from a realtor and were given a range, and somebody came along and was at the absolute top of the range, and although they weren't 100% sure they were going to sell it, they said, if somebody's going to offer me that much, I'm selling my house. Because it's not necessarily that often that somebody will come along and offer you the premium price. All right. So in this particular case, again, the predicted intervals are here. Just doing, again, the math. All right. But we're going to just use the Excel spreadsheet. All right. And here we are. So you can do this but we're going to use the Excel printout for the confidence intervals. And for the confidence interval of the slope, and we're going to use the confidence interval of the y-intercept. Now, the y-intercept in this particular example was not statistically significant. It could the answer that we had was not necessarily accurate, but the slope was considered to be not zero, which is, as I've said a couple times, what we want. So we now know that B0 is the y-intercept and that B1 is the slope. We have, I'm sure you can appreciate the power of this, and it's become much more common because of the power of the technology that we have now to be able to quickly do this for large groups of data, not just a sample of 5 houses or 15 houses. We can do 300. If you were to try to do 300 by hand, the chances of you actually getting the right answer are incredibly small because of all the complex math. But we just put the 300 or the 3,000 or the 300,000 into a spreadsheet and get the results. Let alone we do multiple regression, which we're going to do in the next chapter. So the tedium of the calculations has been taken away. And what's important to understand is what this does, which is determine how the independent variable affects the dependent variable. So how time affects sales, how square footage affects the selling price of a house. And then we read the results. So I hope you enjoy that as much as you can enjoy stats.